Welcome to the CAMS colloquium, which is a little bit different this time, and the audience is also a little bit different this time. But we're very pleased to have Dayung Koh from JPL, who will talk to us about symplectic geometry and astrodynamics. And Dayung actually was a PhD student at USC, not in our department, but knows about our department, and is now working at JPL, and will have a lot of interesting things to tell us. Thank you.
Hi, everyone. I am Dayung Koh. Nice to meet you. It's a big room. I spent about 7 years here at USC for my master's and PhD. And now I work at JPL as a navigation engineer and mission design engineer. Currently, I'm working on Mission Psyche, which is launched on October 13, 2023. It's been flying about 1.5 years. It is a, excuse me. Yes, it's working.
Yes, it's on.
Yes. Wait, check that later.
Maybe you can
Go this way. It is a NASA Discovery Program space mission. And it is a low thrust mission using Hall thrusters, which means the thrusters have the power only enough to lift a piece of paper on Earth that low. So it's very different mission than the conventional chemical propulsion system missions. And, oh, so let's work. And Psyche is on its journey to an asteroid Psyche, named Psyche, which is in a main asteroid belt. Asteroid Psyche is unique because we expect it to be metal-rich asteroid. So Psyche aims to determine if this metal-rich asteroid Psyche is a core of the formal planetesimal, or it is a primordial unmelted metal body, or something else. So we hope, by observing Psyche, we hope we can understand better the planet formation. This is the planar view of reference trajectory of Psyche. Laser works. Oh, wait a minute, so it just stopped working. Okay, this works. So launch from the Earth and going through Mars gravity assist and arriving at Psyche in 2029. So long way to go. And once we arrive at Psyche, we're gonna orbit around Psyche and we're gonna measure gravity, magnetic fields, and we're gonna take some pictures as well.
just to understand the scale, where is Jupiter on this?
Jupiter is far. So at main asteroid belt is in between Mars and Jupiter. And Mars, this is Mars. So Jupiter is about here. And as a navigation engineer, we get the tracking data from DSN and we estimate where Psyche is in a statistical sense. And as a mission designer, we take this navigation's work as knowledge and we design this kind of trajectory as we fly. Do you have any other questions about Psyche? Yes.
What does the gravity assist mean? It means like slingshot, like picking up velocity.
Yes, that's actually a good question. So gravity assist usually helps the spacecraft to get like a booster. So going around Mars, get more the momentum there. So it'll gonna use that extra energy from Mars.
Just in curiosity, it's just like when we talk about a low thrust emission, the reason, what was the reason behind that we're taking this low thrust methodology instead of like the traditional whatever we take?
It's a totally different system, first of all, and low thrust mission using this low power, but it's efficient.
I see. So in this whole mission, it's gonna use this low thrust.
Correct.
I
So Psyche is carrying 4 Hall thrusters, and using low thrust means we're gonna thrust most of the times going on this trajectory. The conventional chemical missions that have like one burn, like, and then just go.
Yeah.
So that's different. I'm gonna get into today's real topic. It's not about Psyche. I'm gonna talk about how the symplectic geometry and astrodynamics collaboration started and where it has gone since. There are many collaborators here, Agustin, Urs, Cengiz, and Otto. They brought the valuable inputs from the symplectic geometry point of view, and they brought all the tools. So yeah, without them, this has been not possible. And I need to mention this from this slide, it's not JPL funded work. It's important.
So it can't be booked.
I summarized my path in a map. So of course it started from USC. Here I studied at the mechanical engineering and astronautical engineering department with Dr. Flashner. I started studying and developing cell mapping method, which is a numerical tool to analyze nonlinear dynamics. I'm gonna briefly introduce about this in a couple of slides. And since then, I was focused on periodic motions and nonlinear dynamics phenomena. And since then, I've been fascinated by bifurcations. Jump onto the right end here. So before Psyche, I worked on Juno navigation. And before that, I worked on Europa lander preliminary mission design work. I would say the core topic of this talk and my research interest and my career all meet at this discontinuity, where I fell into the three-body problem. You're all familiar with the three-body problem, right? It is a classical physics problem about the motion, about the three bodies gravitationally interacting bodies. And what was I going to say? Oh, the equation. Oh no. Okay, so we, as an engineer, we're more interested in the restricted three-body problems where the third body is spacecraft and the mass is negligible. And the motion of equation is described in non-dimensional rotating frame. And I stated here two small masses, non-dimensional small masses here. The reason I pointed here is sometimes as you can see, these are very small numbers. So sometimes for the numerical computation, there are some difficulties. So I wanted to point that. I chose three keywords for my three-body problem study: periodic solutions, mission requirements, and bifurcation. In this study, the periodic solutions are numerically found using cell mapping method. Cell mapping method is a numerical technique to unveil the global behavior of nonlinear dynamical systems. So I would say it's generic and systematic, and it is suitable to analyze global dynamical structures. And I claim that it is easy to apply when for my thesis and all the conferences, but I have my objection to my own statement. Now, it is easy to apply once we have all the setups. So, and I will show you how this setup works in a next slide. So, show you why I have some objections. Oh, and it is, so cell mapping method, it simplifies this continuous time system into the discretized coded map from time 0 to time large T, which is the period that I am interested in. So we're gonna look at the cross section by time variable. I'm gonna summarize the cell mapping in 4 steps. Step 1 is construct the cell state space. For example, looking at this the Europa and Jupiter and Europa system, and for example, for the Europa lander mission, they were interested in to see the orbits going through this area. There, the reason behind, I'm gonna talk about it later as well. So for that, the region of interest will be around here. So technically, the cell state shape of the cell state space or the size of the state space can be anything, but for simplicity, I'll set a box. Once I have that box, we have the upper limit, lower limit, and all the and a grid within that region of interest. And each cell represents a state component, and we're gonna use this cell to analyze the dynamics. Step 2, find the cell map. This is just a toy problem. So I set a region of interest in a 2-dimensional system. So you can see the cell number from 1 to 35. So those those set of integers, we're gonna represent the whole dynamics. And to find the cell map, gonna take each cell's center point as an initial condition and integrate forward for time t and find where it lands, which means cell 1 maps to cell 9. We're gonna do the same for all the cells and find the map. You can see some of them are going out of the region, some are coming back, some are coming back with some steps. So reading or unveil this arrows, that's the step 3, to read all the map. For example, cell number 1 maps to cell 9. So we're gonna follow the arrow. And then you can see the 9 maps to 16, and 16 maps to 17, and 17 maps back to 17, which means 17 is a P1 cell. That means a periodic solution resides in this cell. And all those traces that just belong to in one same group. Moving on to the cell number 2, and you can see they belong to the same group and repeat the same process throughout all the cells. Not for this Hamiltonian system, but you can, in this toy problem, you can see all these cells, or let me say this way, this cell number 17, that's the attractor, all the other cells moving towards 17. So that's what I meant by it for the global analysis. And another interesting thing is with the time t, the large T, one-time integration, you can see this period of P3 solutions. So that's another beneficial using the cell mapping. And step 4 is once we identify the periodic cells, we're gonna pinpoint which point is the actual periodic solutions. So we're gonna correct the point with using the iterative process.
Can I ask a question? So here, if you see this like 3 things rotating around, but because you cut everything into these tubes, these cubes, it might happen that like at some time it's still still rotating around, but at some point it goes out. So how do you work? How do you just exclude these kind of possibilities? Like this is like not an actual period, like a periodic solution, but like something that gradually goes.
Gradually going out.
Yeah, like it's. I mean, it looks like it goes around these 3 yellow cubes, but this is only like an approximation. Like
Yes.
And it might happen that gradually it actually goes to like the cube adjacent to it. And how do you exclude these kind of possibilities? By cutting very small or something?
Okay, so that's maybe that belongs to that claim. It's not easy, so need to refine those cell sizes, and so need to find the right points. So, but for certain dynamics, as you test try and error, you are gonna feel how big step size, the grid size is appropriate.
I see.
So there is no systematic way to determine like the grid size.
So that's a good question. So when I studied this, I set just the uniform grid size, but I think it can be an adaptive grid size, depends on the dynamics around that, like if how nonlinear it is, can adaptively change the grid size, I think.
So there should be some sort of like machine learning algorithms like helping you adaptively determine.
Right. That will be really helpful to set up. And there are many other branches from this cell mapping method. Like they're using some like probability. So so there are other branches from here. So this is the simplest setup. Here are the example results of periodic solutions around Europa using the cell mapping method. I was focused on more the spatial orbits, like in 3D orbits, and was looking for asymmetric orbits as well, because other numerical methods are limited to find those solutions. And there are some other reasons for that too. So looking at this, after I got many solutions, I had questions. Did I find all the solutions in the region? I numerically searched using that cell mapping. If I set the wrong grid size, I'm gonna miss the solution. So genuinely, I had that question. Are they qualitatively different from each other? Just by looking at the solutions, maybe they look different, but if they continue, they might mean something like that. And can they be connected? Where did they originate from? So all those questions. So after finding more solutions, I had more questions.
Oh, sorry.
Go for it.
After.
Go for it.
Oh, my question was, are these diagrams all in the coordinate system where you put the Europa and Jupiter in the same axis? Like, okay, so this is all in that coordinate system.
It's all in that non-dimensional rotating frame. Yes. And another one important question for me, for engineers, what is the right solution for the project? So for that, most of the projects start from a science question. And those mission requirements are derived from the science objectives and physical parameters and observables. So these mission requirements will filter out all those solutions, and they will constrain the selections. Okay, let me give you some examples. So for example, the Europa lander wanted the solution on the far side from Jupiter, because if it's between Jupiter and Europa, the magnetic fields from Jupiter were gonna interfere all the measurements or the views. So wanted on the other side, and I forgot which season. So it has some preferred season to land. So it will control the light condition, and we don't want to have shadow, or for example, we want certain inclination of the orbit, so we can look at the lander from those orbits. So the constraints from coming from mission design. I went off on a tangent here a little bit, but since I mentioned the mission requirements, I'll just go through the mission system space mission life cycle. It has pre-phase A to the operation phase. For example, Psyche is in operation phase, and Europa lander was in pre-phase A. All those mission requirements or operation plan, they're all setting from the pre-phase A, and by phase B, they're like an intense science requirement reviews, and the system design reviews are happening. Let me go back to the real topic here. So we're gonna go back to the solutions, the Europa solutions. So I'm gonna show you some meat of the results. So I'm gonna show you four bifurcation results here. This is H2 family. I call it LPO family. This is a prograde orbit. And the ones that you see here, they're all planar orbits. And as you increase the period here, you can see the energy decreases, and that's plotted here. As you continue this family, we found the period doubling P2 bifurcation at this energy. And how I know it, I found this second root of unity. Well, one of the eigenvalues going through the second root of unity is going onto this real axis. And you can see from top, they're almost on top of each other, but after going through this energy, you can see this planar orbit going up to the spatial little. You can see that motion as you continue the orbit. There's another triple bifurcation here, and same. And I found this third root of unity going through, and you can see visually, I can see that moves from planar to spatial. And for fun, this is the energy, this the center, the spine line, that's the original solution. And as you change the energy, this bell curve line, that's the P2 solution, and the red one is the P3 solution. You can see the period jump here. So you change the energy, one is P2, one is P3.
So these are all eigenvalues of the monodromy
Yes,
matrix
the
that you were
monodromy
saying. Yeah,
matrix,
okay.
yes. So for this study, doesn't matter where this monodromy matrix has computed.
Okay.
I'll go back to the point in the later. This is fun. It's P3 to P3 bifurcation. It is fun. It's hard to describe. So P3 solution, I'm referring to this one bifurcates another P3 bifurcation. Like, doesn't mean it's tripling. It's the same period bifurcation. And can see here, the period stayed the same, but this solution has the much larger eigenvalues. And you can see, okay, this one, the orange one, that's the original P3 solution, and the green one, that's the after bifurcation solution. Yes.
Wait, so this is as you change the energy, 3 orbits becoming 3 different orbits? Like, is that what you mean by P3 to P3?
Nope. P3, I'm referring to P3 is from P1. So the triple period tripling bifurcation happened. So that's P3.
Okay.
So let's use it. The P1, let's say it was period 1. So P3 is period of 3, right? Here, another bifurcation happened from this P3 solution. Period stayed the same. So this bifurcate solution has period of 3, but it bifurcates into another branch. It's getting more confusing. Next one. This P3 solution had the period doubling bifurcation. So it's now period of 6. Let me start from here. So here at the bottom energy here, they look very similar, but as you're changing the energy, you can see this P2 or P3 bifurcated branch, like spread it out. So you can see now the difference in the trajectory. Do I have everyone here?
Is there,
You've convinced us it's complicated.
is there definition of period just a winding number around this? Like what is how do you say it's period 3? Like what are you computing here? Or it's period 1?
So the initial period coming from that integration period large T. For example, I set it's my set. It's T is 1. I wanna find the T is 1 solutions.
Okay.
And then within that branch, I find the bifurcation using that eigenvalues. If it has a period doubling, now its period is 2.
Okay.
So is the period, is it referring to the period of the, in the
Of the-
discretized map, like in the map you get out of this,
No,
The
it's
cell
just
method?
it's the solution of it's
So
the
just the
period of the solution.
so just the actual period, just
Yeah,
the
if
actual
you set,
period of the
if
orbit?
you have this initial condition, integrate for
Time.
time 1, it comes back, that's period 1, periodic solution.
And these are all found using the cell mapping method or some other?
Cell mapping method.
Yeah, do
And
you like keep making the mesh finer and finer, or you just take one mesh and you see everything?
that's a good question. So set some cells, I mean, some cell mappings with certain periods. And some, if I see it all happen, so between this cell mapping results, if I can see that might happen, then continue the family. So using like Newton method, it's just iterative method. It's okay. I knew I'm gonna lose you. But that's the point. So yeah, this is another
Go back to this period. So what does P32 mean then?
P3 is period of 3.
Yeah. Then what does this 2 mean?
Oh, here, that's on P3 to double period bifurcation.
Yeah, what does double period mean? It's like I mean P3 just means it goes back after 3 times this cell method, right?
Right, that
what
means
does
it'll
alpha dash 2
come
mean?
back in 6.
Then what does this actual dash 2 mean?
Oh, that's that's just my notation. So
Oh, so
it
it's like another P3.
mhm,
So,
mhm,
okay, I
that
see.
so
So that 2 has nothing to do with period.
what was
The
that?
number 2 has nothing to do with period. It's just like the second pattern. That's what you mean.
Okay, so one branch, this is P1, let's say, P1 branch. This bifurcates into P3 solution, and this P3 solution bifurcates into another P3 and P32.
Oh, okay. Yeah. Thanks.
These are bifurcation plots, just to convince myself like what's going on. And you can, this is shown in the, where these solutions are going through XZ plane, measure the mean inclination. Maybe this will explain what you just asked. So this spine, that's the original solution that bifurcates into this family, and this one bifurcates into another P3, and this pink one, that's the P32 solution. So I plotted just to show where they are in the energy region. Okay, last one. This doesn't look that complicated. So this one is DRO solutions. I don't know if you're familiar with that. Okay, DRO solution is a very well-known common solution. DRO is distant retrograde orbits. So this is different than the previous one. At here, it's retrograde, means velocity is the other direction, going down. And this balloon on the left side, this is the spine, the original solutions. These are very stable, so it's very preferred to use as a parking orbit. So you don't lose the stability. You're not gonna hit the planet. From this DRO family, as I continue that solution, I found 4 different bifurcations: P3, P4, P5, P6. This is my favorite result. It was very exciting to see. Oh, and P3 and P4, they are planar orbits. P5 and P6, they bifurcate into spatial orbits. And these are all identified, as I'm continuing, identified using eigenvalues. I'm emphasizing this because it's not enough. I can identify the bifurcation will happen, but I don't know to which direction. I don't know how many branches. I don't know. Yeah, so there are many. It's a very condensed information. I submit a paper adding all those plots, rejected. And I can see why I lost everyone here. And after that, yeah, I was sad, but didn't turn me down. I was thinking, how can I improve this? And one of the reviewers said, these are not bifurcations. I clearly show the eigenvalues and clearly compare before and after plots. But yeah, maybe it was too complicated and it was hard to visualize spatial solution bifurcation, spatial to another spatial solution bifurcation. It's too many parameters to show too. So from here, I was more focused on how can I prove bifurcation, and I was thinking about it for a long time. And yeah, and that was not from that was not from my ability. I couldn't cover that. And I came across Agustin Moreno's work on YouTube. And that's how I met symplectic geometry. Let me read this lines. The fundamental question I carry is to understand the global dynamic of behavior and relationship between different families. And this also includes the question, the origin of the orbits. And the important part is that is not obvious from the numerical searches. So having this questions, talking to the symplectic geometry people, we got some tools and have had some important key to find the hidden branch of the bifurcation family, and was able to find some hidden branches and some hidden information using symplectic geometry. One simple example, and was very helpful, was the B signs. B signs is the sign associated with a specific monodromy matrix. So this, I say specific monodromy matrix because it has to be a symmetric orbit. And at the symmetric point, the monodromy matrix, the some matrix of this Wonenberger matrix B, this sign tells us there will be a bifurcation or not. For example, in that symmetric orbit going through this XZ plane twice, and where should I go from here? The eigenvalues of a monodromic matrix anywhere you pick will tell you this has the, let's say, pure doubling bifurcation. But that only happens in one of those points. Not both of the points, only happens on one side. And you can tell which side using B sign. And one of them, we're gonna change the B sign as you before and after bifurcation. And other side, the B sign can stay the same. Yeah, and so I actually apply this information to find the bifurcation of what bifurcation. And the GIT sequences here, GIT sequences, that's the theory. It's a method that Urs and Agustin came up with using Brooks stability diagram, adding the information of the B sign. So it details of the Brooks stability diagram. And Conley-Sander indices, computing the winding number along the trajectory. And that tells you there will be between the families or between the solutions there bifurcation happened or not. So that can be helpful. And the floor numerical invariance. So that this number, I guess you guys are more experts on that. So this number stayed invariant. So after the numerical search, I was curious, or I wanted to know, did I find all the solutions or not? So this floor numerical invariant can tell me, did I find everything from that point? Any questions?
Did you find any? So you were comparing the information that you got from differential geometry with basically what you were doing from the cell techniques.
Right.
So was the answer that yes, there were points that you missed using the cell techniques?
Yes. And the last one that actually helped me to pinpoint one solution. I didn't know that was all, but there was one branch coming to that solution, but it was difficult to continue that solution to meet that point. So I gave up on there. I thought they're not gonna meet. So I left it there, but Urs saw that solution and at this point, you're gonna have 4 bifurcation branches. Wait, I had 3. Hey, wait, I know one was coming to here. So I went back to that and put some effort to continue, and yeah, it was it.
So for that one, did they use the SFT Euler characteristic, or did you have to use something more like
To continue.
like to know that there were extra solutions that you were missing? Like what was the numerical invariant that they
That's what Urs did.
Okay, fair enough.
There was a mention of SFT the characteristic, I think in the previous slide, right?
Yeah.
So
Sorry, I missed your question.
I think there was the mention of the SFT Euler characteristic in one of the previous slides, so maybe that gives a sign. I don't know.
But that didn't take him long, so.
Basically, from the name, I don't know what the floor numerical invariant is.
The expert is here.
I know a little bit about the paper, so I can tell you guys.
Okay.
Yes,
Where did you mentioned the power of the spacecraft, right?
power of the
The
spacecraft.
limited power of the spacecraft, we was able to lift only a piece of paper.
Yes.
Where does it come from? Where does it enter that into everything that you have talked?
Oh, that's for Psyche mission. That's my real job. This work is not related to that. So after Psyche, after I said this is not JPL funded work, separate.
I thought it was related to Psyche.
No.
For like for mission design purposes, like will some of this research like help because I don't know, are you trying to like avoid bifurcations or something because you want your spacecraft trajectory to be predictable or something like that? Like what is the
Yeah, that's a really good question. So the main reason I was fascinated by bifurcation was fun. So I was just looking into it. And for mission design point, so we are using those three-body solutions for mission design. There are some actual applications, like they actually flew to the three-body problem solutions, but it's not that common yet, but they're going. And the reason I am interested in bifurcation in that way is I think using bifurcation trajectories, you can jump from one family to another family using the minimum energy change. Like usually changing that trajectories from one to another, especially different plane, to move to the inclination, it's quite expensive. Expensive means you're gonna use a lot of propellant. But using the bifurcation means you're gonna meet at some point, and with a little bit of change, you're gonna jump to another family. So that's what I am thinking of.
thanks.
Actually, can I just ask like a naive question? So what role do periodic orbits play in like the traditional approach to mission design? Like you mentioned that there's certain orbits are good like parking orbits, and then you're sort of trying to take measurements, but is the typical scenario that you have like a few periodic orbits and you just go on one for a while and then the other one for a while, or what's the general role that they play in that?
Let me give you the example of Psyche. So once we get there, we're gonna orbit around Psyche, and it's not three-body solutions. It's just two-body solutions. We're gonna orbit. It's a circular orbit. We're gonna orbit around it, little far initially because we don't know Psyche. Means if we get closer, we don't know the gravity of the Psyche, or we don't know the shape, or we don't know how it's spinning. So we're gonna start from far. We're gonna measure from far, and once that measure is done, we're gonna lower the orbit and gonna orbit again. And the original plan, I'm gonna tell you about original plan. So it's just keep going down until we're like very low. Is that the question?
But you said these are just two-body.
This one is two-body. And for example, there is a moon mission. We're gonna end on the DRO solution, DRO orbit. So because we don't wanna crash onto the moon. So we're gonna park on that orbit. So make sure it will be on that orbit long time. That's the end of the mission, gonna be there.
I see. I'm just curious, so if you like, suppose you found some really nice periodic orbit, three-body problem that would, like, who gets to decide, like, we're gonna use that one for the mission? Is there like,
That's
so the head of NASA just looks at a list of 100 orbits, says like, I'm gonna go with that mission.
that's the point. That's why I showed you all that the science, the metrics. So the mission requirements and there are many things playing in that game. So usually the three-body problem solutions are not that stable. So, and for the Europa lander mission to execute that plan, we had the plan, okay, we have this kind of crazy looking three-body solutions, but it was too expensive. So we'll cut it to half price, but we cannot do it. So it was halted there. So something like that. It's just there are many driving factors going in. And this decision may be from the mission design lead. Future work. I was thinking about this page for a long time. Question mark. I'm currently working on applying the symplectic geometry tools that we developed there to Enceladus solutions with Cengiz, who is a student of Otto, one of the collaborators. So that's going on, and I'd like to polish the tools for the better accessibility, better usability. And beyond that, I think all the future paths will come from good and persistent questions. So I hope you got all good question marks in your head from this talk today. And that's it. Thank you.
So you said, I think you said before this thing about the retrograde orbits being stable, right, or being good parking orbits. So is there a heuristic for why that's the case? Like why there would be more stable?
Why they're stable?
Yeah, like why are they more stable than the others?
No,
No?
not that I know of.
Okay.
That's a good question. Yeah, wanna know why?
Can you tweak the parameters to see what's happening to the stability?
Oh, that's how I found all the
Yes.
bifurcations. And
But now using the knowledge that you have from differential geometry, can you go back and tweak again and investigate the stabilities?
that would be interesting. Yeah.
Because you seem to live in a curious world that is both very unstable and there are situations that are stable.
Yeah, stable solutions are quite
Unusual.
valuable.
Yes.
So for the parameter you're using here is some sort of like energy, I think, when we're talking about orbit, right? So are these energies, like if you're applying those like symplectic geometric method, like for example, saying like applying those for, I'm trying to applying these floor invariants, you're sort of like, are these notion of energy agrees with those kind of thing, like when saying like in a symplectic setting, you're applying for some like action functional on those orbits as a Lagrangian, and then you're evaluating these kind of thing, and that give you the notion of the energy. Are those things agree?
Yeah.
Oh, okay. So, but the follow-up question is like in the real world, are these energy just simply the kinetic energy of the spaceship?
Yes.
Oh, okay.
Yes.
Okay. Thank you.
It's very interesting. Just kinetic energy, or you have some other terms, right?
What's that?
Is it just kinetic energy or like do you have like
Yeah,
something
do-
from
yeah.
Potential energy.
some potential should be there.
I feel, yeah, that's what I'm thinking. Is it some like, so do you, is like the major term is dominated by the kinetic
Velocity.
energy?
Velocity.
Well, okay,
Which gives you the kinetic energy.
yeah, okay, yeah.
And you expect like in near the bifurcation, you need to change the velocity to something with less cost of propellant. Because it's mostly dominated by the potential energy or something. Like you want to use the propellant when two things are coming together at a point, right? So is there some intuition there?
Like gravitational potential, right?
Something should be big, something should be small, and you are changing the small thing a little. Okay, that was very ill-formed. You don't know what, yeah.
Did you guys write a program to compute the SF2 Euler characteristic, or was that something that Otto just did by hand, or Urs or something? I guess it's not so difficult, probably.
So which one?
This chi SF of x squared. I think it's on the previous slide.
Yeah, it's like.
Like, this is the thing you were.
I see.
This, right?
This one. So this is just numerically computed at the point I have the monodromy matrix
Yeah.
at the point.
This is just something you just calculate direct. You can just calculate.
Yes,
You guys
just
already have the
calculate it.
implementation of that.
Yes,
Okay.
yes.
That's fine.
But the Conley-Zender indices, it's not from me. It's,
Sure.
yeah.
Interesting.
So yeah, that need to be more polished. Any other questions? I have more stickers over here if you want. And thank you.